Hello, welcome to episode 6A. It's an A of multivariable physics. Today we're going to be talking about classifying critical points for optimizations. Obviously this kind of becomes important if we ever have like a function describing the motion of a particle. If you want to know when was its maximum velocity or something like that. You want to be able to find maximum and minimum for interactions and things like that. So being able to classify certain critical points as having, being a maximum or minimum is important. So how can we do this? Very simple. Same way as we can in single variable calculus. We have, sorry, I dropped water, but so we have the first derivative test. So first derivative test. Okay. This is simple. You have some maximum. All we do is we just check sign of all of everything. That's not really, we check sign of all the x's around, and that can be a lot, especially when we're talking about functions in multiple variables. We have to check all the different possibilities. That's not fun. Well, let's not do that. Instead, we're going to focus on the second derivative test. Second derivative test. So how does this one work? Well, the second derivative test, we want to check the sign of the second derivative. So if the second derivative, second d, if it's greater than 0, minimum, less than 0, it's a maximum, and then if it's equal to 0, we have a saddle point. So how can we let's elaborate a little bit more on actually using the second derivative test, because as we've already noted, in multivariable function calculus we have xx, xy, yy, yz. We have a ton of different combinations of these, and these can, there's not a single second derivative, unlike single variable calculus where you have one second derivative because you only have one variable. So let's elaborate on this. So I'm going to use this, do some magic here, and I'm going to say let d equal f of x, f of y, minus f of x, y squared. Now, I should actually notice that. So let's suppose A is a CP. So A f nabla f A equals 0, and then f is equal to f A at, right? This is notation. I'm going to drop the A. We want to find so we have A as a CP. We want to classify it. How can we classify this? So we're going to use this d equals fxx, fyy minus f partial xy squared. And so we have a few things. First of all, if f of x, okay, at A, remember all of these are evaluated at A, or better, remember all of these are evaluated at A. Just want to write that down. So if this is strictly greater than 0, and okay, d at A is strictly greater than 0, right, then A is a maximum. No, wait, no, it's a minimum, sorry, right? 2. Let's suppose x of A is less than 0, and this D here is still greater than 0, then this implies that A is a maximum. And the third case, the third case is D is less than 0. This implies A is a saddle point. And then the fourth case, D is equal to 0. Well, what does that mean? We don't know. It's inconclusive. We can't say anything about whether or not the function is, whether or not this point is a local minimum. So I'm gonna go through this. It's gonna make more sense when I go through an example. So if you remember, earlier I showed this, right? fxy equals x squared plus y squared. So we know that there is a maximum at f of 0 equals 0. So we know that f of 0 is a minimum. Sorry. Or not, yeah, f of 0 is a minimum. So can we check? Well, we can. So what we can do, well, we know fxx is equal to 2, fyy is equal to 2, and f of xy is equal to 2 as well. Alright, no. F of xy is equal to 0. I'm sorry. Right? And so if we actually, and then so what does this mean? Well, D is equal to 2 times 2 minus 0, which is equal to 4. So you are greater than 0, you're greater than 0. Then this means that the vector 0 is a minimum, which is good. That's exactly what we wanted. That's exactly what this said. And you can basically do the same for f of x. For f of x, y equals minus x squared plus y squared. And then this is going to be, so the graph of this looks like this, right? So we actually have a maximum. And so you can actually do the same. Leave that as an exercise. Do this. Prove that 0 is, using this formula, show that 0 is a maximum for this function. And the next thing I want to do is just showcase the saddle point, which, so I'm going to move ahead. I'm going to pick a different color. When I haven't used before, right? X squared minus y squared. I've shown this function off before. This is the saddle point. This is the very stereotypical saddle point. So we should expect that D is less than 0. So what happens if we do this? Well, as expected, f of xx equals 2, fyy equals, and so we know that there's a critical point, so we know the CP 0. I'm not going to check that, but how can we check what the CP is? Well, we just do f of a equals 0, and then so that will give us 2a, 2b equals 0, 0, minus, and then we can solve this equation, right? So you get x equals 0, y equals 0. That's our critical point. So CP is the 0 vector. So our second derivative in y is -2. What is f of xy? F of xy is 0. Right? Xy is 0. And now we want to think about, so what's D? Well, D is equal to 2 minus 2 minus 0, which is minus 4. D is less than 0. So the 0 vector is a saddle point, right? And that matches up with what we know. We know that this is a saddle point. from the graph. So I hope that makes sense. We're going to get into so a bit more examples of using this. And then we're going to take this and then we're going to connect it with what we've also been learning, and then we'll finally look into actually doing some physics.